I would like to now introduce different coordinate systems in 3 dimensions. We have been using the x, y, and z coordinates. These are called Cartesian coordinates, also known as rectangular coordinates. But this is only one way to specify a point in 2 or 3 dimensions. And so we would like to consider other ways that we can specify where a point is located in 2 or 3 dimensions. We're going to start with polar coordinates. So for polar coordinates, we're going to locate a point in the xy plane, say this xy plane, and that point we're going to locate by the distance from the origin, which we will call r, and then an angle from the x-axis, which we will call theta. And so this point can be thought of as either x comma y, the x distance horizontally and the y distance vertically, or r, the distance from the origin, and theta, that angle from the x-axis. And this is just another way to characterize points in the plane. So how do you go back and forth between those points? Well, we can use trigonometry to figure out what x and y are. So we've done this before when decomposing vectors, but x is actually going to be r cosine of theta. So here we're saying that this distance is x equals r cosine theta. And then y is going to be r sine theta. So here we're going to say that this distance vertically is y equals r sine theta. And that's how you can change from polar coordinates, r and theta, to x and y. Now let's say we want to go in the reverse direction. How do we find r? Well, we know, given the Pythagorean theorem, that r squared is actually equal to x squared plus y squared. That's the distance from the origin, and of squared. So if we want to find r, we can just take square roots. And then using trigonometry, the tangent of theta should be y over x. And so we can find theta as being the arctangent of y over x. A couple of things that we should note about this coordinate system is that because r is a distance, r should always be positive. So here we're going to say that r is always greater than 0. And then we have to specify where we want our theta to be located. So here we can say that theta is going to be between 0 and 2 pi. So polar coordinates are just a way to determine each point by an angle and a distance from the origin. Now, what are the advantages? Well, suppose that you want to describe a circle. Well, the equation for that circle in rectangular coordinates is x squared plus y squared equals k squared. But in polar coordinates, we can just specify that circle by the radius. It's all the points where r is equal to k. And that's a much simpler description. Now, what about a line? Suppose I wanted to describe a line. This is actually a half line that goes from the origin out. Well, in this case, we can describe that as all the points that are at a constant angle theta from the x-axis. So we can write that as theta being constant. Well, what constant is that? Well, normally, when we have a line that starts from the origin, it would be the line y equals kx. So, if we want to write that in terms of theta, theta is going to be the arctangent of y over x, but y over x is then just that constant k. So if theta is equal to a constant, that will give us the line y equals k times x. So those are polar coordinates. Now we can take the idea of polar coordinates and we can expand to 3 dimensions, and those are called cylindrical coordinates. So for cylindrical coordinates, we want to specify a point in 3 dimensions. And so the way that we're going to do that, if we want to specify a particular point in 3 dimensions, is that we are going to specify its height, the height of this point, we will call z. And so we will still use that vertical direction z to specify the height. But then in the xy plane, we will use polar coordinates to describe the x and y coordinates. So here we will locate the projection of that point in the xy plane, and that's going to be an angle theta from the x-axis, and that's going to be a distance r from the origin. And so we can locate a point in cylindrical coordinates by knowing its distance from the origin in the xy plane, its angle from the x-axis, and then its height z. So this is essentially polar coordinates in 3 dimensions. X is still r cosine theta, y is r sine theta, and then z is the height z. So again, we have x squared plus y squared is equal to r squared. Tangent of theta is going to be y over x, as long as theta is between 0 and 2 pi. And then z is still z. And so you can think about this as being cylindrical coordinates because the easiest object for us to describe in cylindrical coordinates, of course, is going to be a cylinder. And a cylinder can be described as a constant radius from the origin in the xy plane, and then we can let z vary. Now let's move finally to what are called spherical coordinates. So spherical coordinates are going to be a coordinate system where we're going to specify a point based on its distance from the origin in 3 dimensions and then 2 angles. So here we're going to have a point. That point is going to be x, y, z, and then it's going to be a distance rho from the origin. So rho, or at least rho squared, we know would have to be x squared plus y squared plus z squared because that is the distance from the origin. And then we're going to specify that point using two angles. The first angle is called phi. Phi is an angle that starts at the z-axis and then moves downward through 180 degrees. So you can imagine that you could line up some sort of line segment here, and then you could rotate that line segment down around 180 degrees, up to 180 degrees, and that's going to be the angle from the z-axis. Okay, so phi is the angle from the z-axis. So based on phi, we can figure out how that relates to the z coordinate. The way that we do that is using a little bit of trigonometry. So you can draw this triangle right here. And then that distance there is z. And z, using trigonometry, would have to be rho cosine phi. Another way to think about that is that cosine of phi, okay, using our definition of cosine, should be z, the adjacent side, over rho. Okay, so now using that angle, we can specify the z coordinate. Okay, what about the x and y coordinates? To specify the x and y coordinates, what we're going to do is we're going to drop down this point. We're going to look at its projection in the xy plane. So we're going to look at, if we looked at it from a top view down, where would this point be in the xy plane? Okay, we would look at the point x, y, 0. Now the distance between x, y, 0 and x, y, z, that distance is going to be, again, z. And that z is rho cosine phi. But then this new point that we've dropped down to, x, y, 0, it's going to be a distance r from the origin. And so r is going to be rho sine phi, because if the z in that triangle is rho cosine phi, then using the opposite side from the angle phi, r has to be rho sine phi. Another way to think about that is that sine phi has to be the opposite side, r, over rho. Okay, now that r is equal to rho sine phi, that distance, then we need to find the x and y coordinates. And here we can use polar coordinates to figure out the x and y coordinates. So we're going to pick a second angle, phi. Phi is going to be, sorry, theta. Theta is going to be the angle from the x-axis, just like it has been normally. And so x is going to be r cosine theta, and y is going to be r sine theta. But we're not going to use r in our calculations. So we're going to replace what r is, and r is going to be rho sine phi cosine theta, and then y is going to be rho sine phi sine theta. And so now I can take a point that's described by a distance from the origin, that's rho, and then two angles, phi from the z-axis, and then theta from the x-axis, and then I can describe x, y, and z coordinates. So if I want to go from the x, y, and z to the spherical coordinates, I've filled in already what rho squared is and what phi is, because cosine phi is z over rho. Tangent theta, again, is going to be y over x like it was for polar coordinates. So theta is going to be an angle that's between 0 and 2 pi. And phi is only going to be an angle between 0 and pi. And that's because if we let phi go all the way around to 2 pi, then we would be double counting some of the points. So this is, these are spherical coordinates. The most natural thing that you could describe in spherical coordinates would be a sphere. So if you want to describe a sphere in spherical coordinates, okay, that's all points that are a specific distance from the origin. We'll call that distance, say, k. And so rho equals k, that's going to be just the specific, all points that are a constant distance away from the origin. That's going to give us a sphere.